Hello everyone. In this video, we are going to be looking at a spherical shell with a uniform thermal conductivity that has an inner radius of 1 meter and an outer radius of 2 meters, sorry. At 1 meter, the temperature will be 100 degrees Celsius, while the outer surface is going to be 0 degrees Celsius. And we're going to ask the question, what is the temperature of the radius at 1.5? So let's go ahead. I'm going to draw this diagram here to kind of visualize the question that we're answering here. So let's start with the inner radius. We know that from this point that this is 1 meter. What we also know is that at this point it is 100 degrees Celsius. So that's what we're told. Now for the outer radius, we're told that it is 2 meters and that it is at 0 degrees Celsius, right over here. I'm going to draw this a little better. 0 degrees Celsius. Okay, so how do we solve for any temperature that's in between? Well, if we have our boundary conditions and we know the temperatures of our boundaries, something that we can do is we can do something pretty intuitive. We can say, okay, I can solve with Fourier's law the heat and the energy between 1 meters and 2 meters. And then I can relate this energy to anything in between so that I may be able to find uh, any temperature in between radius 1 and radius 2. So let's go ahead and actually begin writing this equation. So for Fourier's law, we are going to say Q equals negative thermal conductivity times the area multiplied by some temperature gradient. And we're going to put D of R for change of radius. So let's go ahead and change this area. The area of sphere epsilon is 4 pi r squared. And okay, yeah, that looks good. Okay, so now that we have this equation, what are we actually looking for in this? Well, what we're actually looking for is we're trying to find some conceptualized relation of Q to other temperatures in between the first radius and the second radius. So what we're actually going to do is begin a separable equation and integration to then find Q in this case and its relation between the inner and outer radius. So what are we going to separate? We're going to separate our differentiation of temperature and radius. This is a lot easier than it looks like. So to start, we're going to go ahead and try to get temperature on its own on one side, and we're going to get anything radius related into the other side. So I'm going to start off by, to get T by itself, the easiest way would probably be by dividing the thermal conductivity and the area and multiplying by the change of radius to the side of Q. So if we do that, we have Q multiplied by 1 over, this would be negative K multiplied by 4 pi r squared. And then we're going to multiply this by differentiation of radius. And then we're going to set that equal to the change of temperature. So if you've done calculus 2, this should look pretty familiar. Just looks like a separable equation. So what I'm going to do is put anything not related to r in front because it's just a coefficient. We're going to put q negative k times 4 pi. We're going to multiply that by d of r squared, d of t. And now what we can do is begin integration. And this is easy because we're actually given the bounds for both of these integrals. For the radius in this case, we have the inner radius, which is at 1 meter. That's the beginning. And then we have our outer radius, which is 2 meters. And then we have our D of, we have our change of temperature, and we know that initially it's at 100 degrees Celsius and that it goes to 0 degrees Celsius. So integrating, the integration of a constant is just going to give us T. So we're going to get, in this case, this would be 0 minus 100 degrees Celsius. And then over on this side, we're going to do the integral of 1 over r squared, which, if you don't know, is, do I even know? That's a good question. Uh, this is negative 1 over r. That is the integral. And then we're going to have our bounds be from 2 to 1. So we are doing from negative 1 over 2 minus 1 over 1, which would give us, is that right? No, this would be plus, sorry, which is zero point 0.5. And then we're going to multiply that by q negative k times 4 pi. And something we're going to do here, just to make sure our math actually makes sense, I'm actually going to go ahead and shift this negative over to zero point 0.5. So I'm going to do that by raising the negative here. And I'm just going to shift it over to negative zero point 0.5. This is because if we divide the negative zero point 0.5, or we divide the negative 100 by the negative zero point 0.5 over here, we get a positive temperature of 200 degrees Celsius, which makes a lot more sense quantitatively over here. So we have 200 degrees Celsius. We're going to set it equal to Q over K times 4 pi. Okay, so now this is just kind of plug and play. We can say that Q now equals K times 4 pi, or did I say K? Q equals K times 4 pi multiplied by 200 degrees Celsius. So notice that's still not really an answer because we have thermal conductivity and we don't know what that is. So how could we possibly relate that to the temperature at 1.5 meters a second? Well, let me go ahead and show you how we can do that. If I can figure out how to expand this. Hmm, here's what I'm going to do. I'm just going to go ahead and shrink everything. There we go. Okay, so we have this equation for Q. So how do we relate this to 1.5 meters for radius? So here's what we can do. I'm going to go ahead and just kind of quickly visualize what we're solving for. My pen is acting up. Okay, so if we try plugging the equation like how we did for the previous one, we're going to get something like this. We're going to get, and I'm not doing anything different. I'm just repeating the steps that we did for the previous solution of 1 to 2 meters. This is the same separable equation. So now our conditions are going to look a little different. This radius is not going to go from 1 to 2 meters. It's going to go from 1 to 1.5 meters because that's our new boundary. And for the temperature here, we have the initial temperature of 100, though we don't know the temperature of the final. We don't know the final temperature of this, so we're going to leave this as an unknown variable. So now what we can do is begin integration, and if we do this, we'll have 1.5, it'll be 1 over 1.5 meters minus 1 over 1 meters, which is equal to, let's see, just would be temperature final minus 100. And this is being multiplied by Q over negative K times 4 pi. Now, if you've noticed, if we have this Q over here, what we can actually do is plug in this Q that we solved from the initial and final temperatures of the inner and outer radius and plug them into Q over here. And when we do that, notice we don't have to know thermal conductivity anymore. We can cancel that out. We're not concerned about 4 pi, and we're left with 200. So actually we have negative 200, negative 200 degrees Celsius multiplied by, now let's see here, have to do some more math. We got a calculator. I am just going to use Desmos really quick because my calculator is dead. Desmos, I'm going to go ahead and put 1 over 1.5 minus 1 over 1. And that's going to give us negative 1 over 3. And now we're going to multiply this by 200, which equals negative 66.7. Now we're going to set this equal to temperature final minus 100 degrees Celsius. And now we're just going to add 100 degrees Celsius on both sides. Calculate this. And this equals temperature final equals 33.3 degrees Celsius. And that is how we can get the temperature in between the outer and inner radius by relating some Q that we find by using Fourier's law to then use this as a constant to plug in into our new equation relating to the 1 meter inner radius and the 1.5 in between radius that we were curious about.